Alright, let's take a look at another application of derivatives and optimization. So here in our question we have two pens with one common side are said to be built with 60 meters of fencing. One pen is to be a square, the other rectangular as shown. Find the dimensions and maximize the total area. So we can understand that our pen kind of will look like this. Okay, so basically we have this partition and we have two different regions of that pen, right? And one is a square and the other one is a rectangle. Now we can do this one of two ways, right? We understand that if I let this represent the width of the rectangle and this the length, right? Then this would be a width, this would be a width, this would be a width, and this would be a width, because this region here should be a square, right? So we just don't know what this value here is. We can call it x, but we can figure that out afterwards, right? We have x plus w is equal to length, right? But we can understand that if this is a length and then this is a width, right? I just wrote that twice. But in this case, the perimeter is 2 times length plus 3 times the width, because there's going to be 3 widths here, right? Because you're going to lay down a foundation or partition here, here, like you're going to lay down fencing all of there, right? So the amount of fencing, the perimeter, the amount of fencing that you've laid down here is 2 times the length plus 3 times the width. Okay, and this should be equal to 60 meters of fencing, right? Now what we want to do, we also understand that the area, the total area, is length times width. So what we want to do is we want to create a function of area with respect to one variable. So in order to do that, what I'm going to do is I'm going to do a substitution. So the perimeter, once again, is 2 times length plus 3 times the width is equal to 60. And I'm going to do a substitution for one of the variables. So in this case, 2 times length is equal to 60 minus 3 times width. Right? And you can pick length or width, it doesn't matter. And what I'm going to do is I'm going to divide this by 2. I'm going to do the same thing for both of these. So the length here is 30 minus 3 over 2 times the width. Okay, so this is their length. What I'm going to do is now I'm going to substitute this into equation 2. So now area is equal to, instead of writing length, I'm going to write 30 minus 3 over 2 width times the width, and then if you expand this guy out, area is now a function of the width, and you get 30w minus 3 over 2 w squared. And if you want to find the width to create the maximum area, let's find the first derivative. So I'm going to find a prime of w is equal to 0. So a prime of w here is equal to, I'm just going to find the derivative of this, so you get 30 minus 3w, right? And if I let a prime of w equal 0, you get 30 minus 3w is equal to 0. I'm going to move this to the other side, so you get negative 3w is equal to negative 30. And the negatives would cancel out, and w here is equal to 10. Okay, so if w is equal to 10, what we also need to figure out, so this is the width to make maximum area, we also need to figure out the length. In order to figure out the length, I'm going to substitute this back into, so I'm going to substitute this into equation 1 to solve for length, and then this is going to give me 2 times the length plus 3 times 10 is equal to 60, and as a result, you get 2 times the length plus 30 is equal to 60. I'm going to move the 30 to the other side, so 2 times the length is equal to 30. L is equal to 15. Okay, so in this case, we have a length of 15 meters and a width of 10 meters. Now we also need to find the dimensions of the smaller rectangle. Well, we can understand that because x plus w is equal to length, x is equal to length minus w, x should be equal to 15 minus 10, which is 5 meters. So if you look at the dimensions of each of these rectangles, these rectangular plots, right, you can imagine this is 5, this is basically 10, this is 10, this is 10, and this here, this region here would be 10 as well, and this whole thing would be 15. This would create a maximum area. If we want to figure out the maximum area, right, so the maximum area would be the width times the length, which would basically be 10 meters by 15 meters, right, and that should give you 150 meters squared, right? So therefore, the dimensions of length 15 meters by width whoops, 10 meters will give a maximum area of 150 meters squared. Okay, so this would basically be how we can optimize our maximum area for this scenario. Okay, so it's really important to understand how to create a function by using substitution, and after you're creating the function, you can just kind of use the first derivative to optimize. Very straightforward.